All creatures have ancestors, even these puppies. Biologists classify organisms into groups with similar characteristics, consistent with biological relationships. Think of a classification structure as showing sets of relationships. Subsets belong to a greater set. This is a Schnauzer, a breed of the dog species, which is in a family of related animals called Canidae. It includes wolves, coyotes, and foxes. This family is part of larger and larger classifications. With a group so grand, a diagram is one way to keep track of the relationships. Look at this rational number diagram. Did you get all that? Rational numbers are numbers that can be represented as a fraction, a over b, in which a and b are integers and b is not zero. The set of rational numbers includes subsets of integers and numbers that can be represented as decimals that are terminating or repeating. Every rational number can be written in one of these forms. That sets you up nicely. Let's look further at rational numbers. Let's jet to Europe and visit Paris, France. But if you're used to American shoes, the European sizing might baffle you. Those shoes you've been eyeing look like they'd fit, but the size numbers are way off. That's because European shoe sizes are scaled differently from American sizes. Let's say that in the American system, you wear a men's size 4.5 or a women's size 6. In France, that would be a size 36. The shoes would be the same size, except for how different systems express the size. We can also express whole numbers in different forms. The number 36 is the same as 36 over 1 and 36.0. Even though we can represent them in different ways, the quantity is the same. So on a number line, they have the same place. We can express rational numbers as fractions, with integers for the numerator and denominator. But the denominator can never be 0. Therefore, 36 is a rational number because we can express it as 36 over 1. It's the same for any integer, including 0. They all can be expressed as a fraction with themselves as the numerator and 1 as the denominator. This goes for 0 also. Integers include 6. This is the American women's size equivalent to the European size 36. 6 is 6 over 1, another fraction that fulfills the requirements of rational numbers. We can make another equivalent fraction by multiplying both the numerator and denominator by the same integer. For example, 6 is the same as 6 times 2 over 1 times 2, or 12 over 2. That's another way to represent 6 as a fraction. We can represent any integer as a fraction with itself over 1, or as an equivalent fraction with a multiple of the numerator and denominator. Therefore, integers fit in the group of rational numbers, including negative integers, even though shoe sizes aren't negative.
Perfect!
And remember, if the shoe fits, wear it. Humans, dogs, and even chimps live in groups. Each individual in a group is a part of the whole group. For example, in this very large family, the parts are 2 parents, 9 boys, and 5 girls. 16 people altogether. They make up the entire or whole family. We can consider parts of the family using fractions of the whole, with 16, the total number of members, as the denominator. For example, the parents make up 2/16 of the family. Both the numerator and denominator are even, divisible by 2. So we can simplify and divide each part by 2 to get 1/8. These fractions are examples of rational numbers. Those are numbers that can be expressed as a fraction with an integer as the numerator and an integer other than 0 as the denominator. Why not 0 as a denominator? A fraction can represent a division of things into the denominator's number of equal parts or groups, with the numerator representing how many of those parts you're talking about. You can't divide something to form 0 parts or groups and still have the whole thing. Nothing would be there. So 0 cannot be the denominator of a fraction, nor of a rational number. Anytime you add, subtract, multiply, or divide two fractions, you get another fraction, another rational number. Here's a simple example. Add parts of the same family. You end up with another part, a fraction that's also a rational number. The boys plus the girls are 9/16 plus 5/16 of the family, or a total of 14/16, another fraction. Whenever you do arithmetic on rational numbers, you end up with another rational number. That's a full house. Baseball is an American pastime. You might not have thought about this, but batting averages are rational numbers. A batting average is the number of hits, H, divided by the number of at-bats, A. It's a fraction. But wait, if you're familiar with batting averages, you know they're expressed as three-digit numbers with a decimal point. But what if the decimal version has more than 3 decimal places? What if the player had 25 hits in 80 at-bats? That's 25 over 80, which has a decimal version of 0.3125. We round it off to 3 decimal places, a batting average of 313, meaning thousandths. Let's look at some complete batting average decimals before they're rounded. Now, what if the player had 30 hits in 90 at-bats? 30 over 90 is the same as 3 over 9, or 1/3. The decimal equivalent is 0.3333, and so on forever. Until now, we were talking about decimals that ended, called terminating decimals. This one repeats over and over. That's a repeating decimal. It, like any decimal, can be rounded to a number of decimal places, including the 3 we need for a batting average. That's 0.333, or 333, meaning thousandths. A batting average before rounding could have different digits repeating. For example, if a player got 26 hits in 111 at-bats, the decimal version of 26 over 111 would be 0.234234, with the 234 repeating forever. We'd round to say the average was 234. Since a batting average is a ratio of 2 whole numbers, hits to at-bats, and the denominator's never 0, it's a rational number. We can express this ratio as a fraction and either as a terminating or repeating decimal. When we convert this decimal to one with 3 decimal places, tenths, hundredths, and thousandths, we've got our batting average. Play ball.